I'm going to briefly describe how to use an interactive simulation that leads you through the steps in the McCabe-Thiele method for a distillation column. And I've indicated here where you can find this simulation. So let's look at one snapshot of the simulation. So simulation is plotting the vapor mole fraction, the more volatile component, in this case methanol, versus the liquid mole fraction, that component. This is the x equals y line as the reference that we use. The values for this simulation, some are fixed. CF, the feed, is mole fraction of 0.5. The value of the liquid, we collect the distillate, where D is the distillate flow rate, is set at 0.85. And the value of the bottoms is set at 0.05. The vapor flow rate, coming up liquids, what's returned to the column, that's for the upper part. The rectifying part and the lower part, the vapor notation like that with a line over it, and the liquid flow rate is like that. So that means that this is the vapor flow rate in the bottom part of the column, the stripping section, liquid flow rate, and B is the flow rate of liquid that we're collecting out of the bottom. And then on the plot, the orange line, this is the mass balance for the upper part of the column, rectifying. This is the mass balance for the stripping part of the column. This is the relation between y and x for vapor-liquid equilibrium for this mixture is non-ideal, and details are explained in the simulation. And then this line, so ZF is here, and XD is here, and XB is down here. And this line slope is changed by changing the quality. So if quality is equal to 0, then that corresponds to a vapor at its dew point, and quality equals 1, so that vapor is a liquid at its bubble point. It can be greater than 1, supercooled liquid. It can be less than 0, superheated vapor. So this is a total condenser, meaning this composition is this, which is, so this Y value going in this case it would be Y1, would also have the same mole fraction as XD. Well, let's look at the top part of the column. So let's look at another snapshot where we're going to have some of the stages drawn in. And you can see selected here the stages that we're going to count, and we use a slider that steps in increments to count. And we'll show in the simulation how we go through each of these steps. What I want to do here is point out the mass balances. So let me label things again. So I've indicated liquid flow rate, so L is a molar flow rate. Liquid flow rate's down, vapor flow rate is up, and D is the distillate flow rate. If I were to write a mass balance around this dotted dashed purple section, then what's coming in is Y3 times the molar flow rate, so mole fraction times the molar flow rate, number of moles coming into that. And what's leaving is two places, liquid flow rate going down times X2 plus the distillate flow rate times XD. Well, I can generalize this, and I can rearrange it slightly by dividing through by the vapor flow rate. Yn plus 1 equals L over V times xn plus d over v times xd. So this then would be the slope of this line here. And so let's label these again. L, that's vapor. So the vapor is L plus D, which means L over V is less than 1, so the slope is less than 1 there. And so this mass balance applies the upper part of the column, and so we have to satisfy that at these points. And then equilibrium, so x1, y1, x2, y2. Leaving a column, so look at this stage here, leaving a stage, y2 is in equilibrium with x2. y1 is in equilibrium with x1. You can see from this mass balance, this point is x1 and y2, this is x2 and y3, and that's why they fall on the mass balance line. Let's look at one more snapshot. Well, now I'm doing a balance in the lower part of the column. And so, again, a balance, this purple area And what's coming into the system, as defined by that purple dashed line, should equal what's leaving for our more volatile component. So entering X3 times L with a line over it, and what's leaving is Y4, vapor flow rate, and then XB times the bottom flow rate. Well, let me rearrange this. So this is a mass balance. Of course, I can generalize it for more stages. This is then the equation for this line, because those points have to fall on X3 and Y4 has to fall on the mass balance line. Well, also notice that because that liquid flow rate coming into the bottom is split up into vapor and the bottoms, that means that the slope of this line, L over V, must be greater than 1, as you can see on the plot. So let's look at the simulation briefly. So here's the interactive simulation. And the idea is for you to step through. You notice right now it's selected the plot points, and it shows the feed. There's the distillate. There's the bottoms. Next step is to draw the operating lines. And so this is showing the feed. I can change the quality, and that's going to change the slope. And the diagram on the right shows then how the feed is distributed. Partially vaporized feed, some of it goes into the liquid stream, and some of it goes into the vapor stream. So by selecting that, it shows now the slope that we talked about previously for the operating line, and then the diagram corresponding to that. If I select the bottoms, the stripper part, again shows this mass balance that we derived, and the purple line indicating the slope. If I count stages, and what it does is the slider only, of course, goes to integer values. The first stage, second stage, where remember we are using this point for X1 and Y1, phase and equilibrium. This point is the mass balance that we derived. This point is also mass balance. And I can step through to get to the bottom. That's also a stage, the reboiler. And then it shows where the optimal feed location is for this particular system. So very brief, but hopefully gives you an idea of how to use this interactive simulation, change the quality, and see how that affects things.